everyone. Today is Halloween. I tried to suggest to my daughter to dress up as the shadow of a black hole in celebration of the latest data from the event horizon.
The scariest thing you possibly think
But
of.
she didn't accept the suggestion. I just want to remind everyone we have these forums that we have every week. One on Mondays, Faraz is organizing the philosophy forum about singularities, and it's going very well as far as I hear. At 11 a.m. and then on today we're supposed to have the LIGO science forum. Where is the thing?
Today's canceled.
Oh,
she's away.
Not around today?
She's traveling.
Okay, so she did cancel it today?
Yes.
Okay, so next week.
Right.
Who is making the presentations today? Go ahead. Please come over here.
Sure. So today we're joined by Shadi Tahvildar-Zadeh. He's a professor of mathematics at Rutgers down in New Jersey, and he'll be speaking to us about GR at the atomic scale.
Thank you so much for this opportunity. And here's my Halloween costume.
By the way, it's being recorded.
Yes. Did you catch it?
I did, very clearly, yes.
Send it to the White House. Okay, so I'd like to talk about some recent work with my colleague at Rutgers. I have, these are a series of papers that have appeared in Journal of Mathematical Physics and Journal of Physics A, and there's older paper of mine in Review of Mathematical Physics, and also the thesis of my student that's available through Rutgers. I won't be able to go into any details, so just for you to know that all this is published, and if you're interested in details, talk to me afterwards or can show you the references. So general relativity and quantum mechanics. Are there incompatible worldviews, as Dyson says, or are they pieces of the same puzzle? There are many statements out there regarding these two theories. Some of the most common ones are the following. These are two beautiful theories that should never be combined. And general relativity applies in the large, and quantum mechanics applies in the small. Of course, given the recent discoveries in gravitational waves and how it was made, where the gravitational waves coming out of the universe move something by the width of a proton, this is a bogus reason for not to combine these two things. And general relativity tells us about the past, quantum mechanics tells us about the future. So, you know, this is the kind of a statement that if I make it, they will put me in the nut house. But when Dyson said the same thing, everybody clapped. I was there, actually. This was for the 100th anniversary of the discovery of Einstein's equations, where he made that statement. So my colleague and I have a different approach. The question we are asking is, do these two theories have a common mathematical problem, perhaps, that can best be addressed by putting them together, like two pieces of a puzzle? So that's what we are trying to do, or see if it makes sense. And what we think this common problem could possibly be, there is a fundamental issue in all of physics, no matter what kind of physics you're interested in, and that's the issue of singularities and their motion and propagation. So this has been something that is becoming more and more an active area of mathematical physics, just because the mathematical tools to study these singularities are more available now than they were, say, 50 or 60 years ago. So what are these singularity problem in GR? So Einstein and Rosen wrote a paper which nowadays is enjoying a second life. This is called the so-called bridge paper, in which they glued two copies of Schwarzschild solution, exterior Schwarzschild solution, at the horizon, And in this way, they accidentally discovered half of the maximal extension of Schwarzschild, long before Kruskal and so on. However, their motivation, why did they do this? The title of the paper is The Particle Problem in General Relativity, and what Einstein and Rosen were after. When you read this paper, and I recommend you to read it, although there are a lot of things in it that are actually wrong and even wrong-headed. But the idea was to find a solution of Einstein's equation that can model a particle in the sense that it's localized. And the big obstacle for them was this idea that they didn't want, or Einstein didn't want his solutions to have any singularity. So they thought that by copying two copies of exterior Schwarzschild together, they would get something which has no singularity at all. And at the same time, it's something that's localized because this horizon is still sitting there, and that will be like the particle in this space-time. So that's the kind of thing that we would like to start from. There are two things that are interesting in this paper. One, for the first time, as far as we can see, there's this idea that particles can be represented within general relativity as bridges connecting two vacuums. These wormholes, although they didn't use this term, but that's what it would be called today. And the other idea was that a space can be multi-sheeted, like a 3- or 4-dimensional version of a Riemann surface, where, and this is the way they were thinking about it, because this space, after you're done with this gluing, your space has two sheets. And so that's, so those are the interesting aspects in this paper. Of course, they did not really succeed in doing what they wanted, and I think that one of the main reasons was that there was this mental block that you do not want to have, you don't want to deal with singularities at all. You're looking for things that are smooth everywhere and no singularities, and nature doesn't seem to be like that. But there were other people, on the other hand, at the completely opposite view, or the opposite extreme, which were that the singularities were everything, in fact. And Hermann Weyl most famously had this theory that, in fact, that's what matter is. Matter is, particles of matter are singularities of the space-time. That's an idea of Hermann Weyl. This in his famous book. And when you read what he's talking about, he seems to be suggesting that the particle is, in fact, a singularity of a space-time. And more dramatically, these singularities need to be excised from the space-time. So, in fact, to put it glibly, matter is where space isn't. And so what's common between these two approaches, even though they're quite different, is that perhaps there is a topological resolution of the singularity problem. And why do we say that? It's because these spaces are going to have non-trivial topology. In the first case, you have something which is multi-sheeted, so like a Riemann surface. And in the second case, you have these space-time from which you have excised many tubes, many one-dimensional curves, time-like curves. And so this gives you a highly non-trivial topology to your space-time. And you're supposed to be getting physics out of that non-trivial topology. So this is the kind of things that people were thinking about, although it didn't really go anywhere. And Weyl also changed his mind about that several times. And perhaps the tools that would be needed to study these spaces weren't there at the time that these guys were thinking about it. But now we have more tools. So we can revisit these problems and think about these things. So that was the singularity problem in general relativity. In classical physics, there is also a singularity problem. The most famous one is in electrodynamics. So electrodynamics, as described by Maxwell and Lorentz, charges and currents are sources of the electromagnetic field. This was Maxwell. And then electromagnetic field acts on charges and makes them move through a mechanism called the Lorentz Force. So that's, now when you put these two together, you get a problem. Because for point particles, the electromagnetic field generated by a point particle is not defined exactly where you need it, namely at the location of the particle. So when you try to couple these two things together and study the joint problem of evolution of fields and particles, you start having this kind of a problem, that you have an equation which, for example, describes the conservation of momentum. This T mu nu is the energy momentum tensor. And here, what I have here, in terms of physical quantities, the time derivative of the momentum plus the divergence of the stress. This is supposed to be equal to 0, and that would be the conservation of momentum. When you have these singularities in your theory, the right-hand side becomes a delta function concentrated on the path of the particle times some function of x, which would be the force on the particle, except the problem is that this force is precisely undefined on where the particle is. So therefore, the right-hand side of this equation doesn't make mathematical sense. You cannot study this even as a distribution. If you had a finite thing here, maybe you could do that, because you would integrate, and the delta function would go away, and that would give you some notion of the force. However, this doesn't work in the classical electromagnetic theory. This doesn't work. And so now, what do you do? Then the problem that's sort of a consequence of that, one of the consequences of this, but one main consequence is you cannot do a joint problem because the equations of motions, you cannot make sense of them. The other problem is that the self-energy of the point charge is infinite. So a single point charge, its electrostatic field is given by the Coulomb potential, and the energy, electrostatic energy of that is badly divergent. It's not even close. So that's so. Now you should note that you may think, oh, I'm just going to smear this and make it into a blob, and then do my physics, and then take the limit as the blob goes back to a point. This doesn't work because it depends on what kind of averaging and what kind of smearing you do. It's not independent of that. So mathematically, is not a good solution. These problems are inherited by the quantum theory. So these infinities that are in there in the classical theory are just inherited by the quantum theory. The quantum theory can't get rid of these things.
In practice, all we do is we ignore the self-force.
Yes, yes.
And look at the force from everybody else, and everything works.
Yes.
But you're
Yes,
saying
but I'm going to
is,
say why it's not going to work.
It's-
Yes,
oh,
right,
okay.
right. So I'm going to say, yeah.
But there is something that doesn't work, which is the self-force.
Yeah.
There is this whole issue of positive and transcontention.
Yes. Yeah, there are ways of it.
Okay.
There are ways of that. So of course, you will see the next slide why things will start to go badly. So these problems are not resolved in a mathematically rigorous way by current known extensions of quantum mechanics. So all these infinities, and you have to cut off, and series are divergent, and so on, and all of that has to do with this infinity at the classical level. Is there. So now, as you said, in practice, we could ignore the self-force and everything would work. However, we want to couple it to gravity. You want to couple it to gravity now, unfortunately, you cannot ignore the self-force anymore, because this object, remember this T mu nu, that's the same one I showed you. This shows up at the right-hand side of Einstein's tensor. This is how you couple things to gravity. And now you have on this side something which doesn't make mathematical sense. And therefore, if you want to put it in physical terms, this will generate an infinite tidal force. So it will tear your space-time apart. So even a single point charge is going to do that. So that's, as a result of which, when you look at known solutions of particle-like solutions of Einstein-Maxwell, what you would expect to be a particle-like solution, namely just a single point charge, right, being the source of everything. And it turns out that these solutions are highly, highly singular. In the parameter regime corresponding to elementary particles. So these solutions depend on certain parameters. One is called the charge of the particle, the other one or of the space-time, the other one is the mass of the space-time. And these space-times, if the ratio of the charge to the mass is less than 1, they have black hole solutions, they have a horizon. So at least we can ignore what's happening inside the horizon. And we say, okay, we're going to stay outside, we don't see any of the bad stuff. Unfortunately, the ratio of the charge of the electron to the mass of the electron in the wrong units, it's somewhat bigger than 1. As you can see. So this does not work. And at least if you're looking for a particle-like solution, which again, this is only one thing that you can do, but this is what Einstein was interested in. So we are just trying to see whether what he was thinking of is possible at all. So these solutions, by the way, you may know, I don't know in this audience, you probably are familiar with Reissner-Nordstrom. That's the solution of Einstein's equation, which is spherically symmetric and static. And that solution has this problem. And then the axially symmetric, stationary axially symmetric solution is known as Kerr-Newman, and it also has the same problem. So the fact that you do or don't have angular momentum does not play a role. It doesn't fix anything. So that's how it is right now. And the question is, what can we do about this? And in particular, what is going to happen if you try to do the quantum version of this problem? This is almost classical physics, right? You're just trying to couple classical electromagnetism to gravity. So now, it is true, again, as that if we try to ignore these issues, it's not like we can't do anything. In fact, we can do a lot. So for example, this is the problem. This is one of the successes of relativistic quantum mechanics, is the hydrogen problem. So in the hydrogen problem, you have a proton, and you want to imagine that I'm going to make hydrogen. So I need to put an electron close to the proton and hope that they bind and they give me a hydrogen atom, right? And because the mass of the proton is much larger than the mass of the electron, I could imagine that the proton is just fixed there, right? And the electron is the only one who is doing all the work, and therefore reduce the two-body quantum mechanical problem to just a one-body for the electron. This is called the Born-Oppenheimer Approximation. In this approximation, the hydrogen problem reduces to the study of the Dirac equation with a Coulomb potential, the Coulomb potential coming from the proton. That's at the center. So you would like to study this problem and see if you can get the orbitals of hydrogen coming out. So take the Dirac equation, which looks like this. Psi is the wave function of the electron. H is the Hamiltonian. It has a two-part, has a free part. That's the free Hamiltonian, Dirac Hamiltonian. And you need to add this potential to it, coming from the electrostatic force of the nucleus on the electron, which is like it is. It's a singular function. So that's and then one of the first thing you need to check is that this singularity there does not create a big disaster for you. So to put it mathematically, you have to make sure that this Hamiltonian is essentially self-adjoint. What that means is that there's only one way that you can make it into a self-adjoint operator. Because you want to study as a spectrum, therefore it needs to be a self-adjoint operator, and it has this singularity, so you need to think about this domain and so on. And the question is, do we need to now assume that we have some boundary condition at this singularity or not? If you are free to put some boundary condition at the singularity, that then who would tell me that boundary singular? Who would tell me that information, right? That would be something that's not essentially self-adjoint, and that's not good. So one of the first things that one proves in this business is that this Hamiltonian is essentially self-adjoint as so long as this constant is not too large. And that's so once that is done, then you can study as a spectrum. And in fact, this study by studying eigenfunctions, you make this ansatz and reduce it to the eigenvalue problem. And then you study the eigenvalue problem, and lo and behold, the discrete spectrum comes out, and it's very nice. You can even write down a formula for it. And this formula was in fact known before Dirac wrote his equation. So this is one of the great triumphs of Dirac, was that he came up with this new equation, and then the Hamiltonian ended up having a spectrum which was exactly the Sommerfeld's spectrum relativistic generalization of Bohr's spectrum, which depends on two integers, n and k. This is the main quantum number. This is the so-called Sommerfeld quantum number, or the azimuthal quantum number. And so this is one of the great successes of relativistic quantum mechanics. And one of the questions we want to ask is, can I put gravity in this? So, and when you think about that, you should think in terms of physics. That's one of the first things we learned in physics, right? That gravity is much, much weaker than electromagnetism. If you learn your physics like I did from Feynman's lectures on YouTube, in one of his lectures, he says, yeah, you know, it's very easy. You pick up an object. When you pick up an object, the entire Earth is pulling on that by the force of gravity, and yet your muscle can overcome the entire Earth. This is because the forces in your muscle are of electromagnetic nature, while that one is just gravitational. So that sort of proves for you, as far as physicist is concerned, that nothing should happen if you try to throw in gravity in this. Okay? And it's true, if you would throw in Newtonian gravity in here, nothing would happen. But excuse me, we cannot throw Newtonian gravity into a relativistic theory, right? We have to put in relativistic gravity, which means we need to put Einstein's equation in there. And then all hell breaks loose. So when you want to try to do general relativistic hydrogen, you start by thinking that nothing should happen, but then when you actually try to do it, you have to take Dirac equation, and you need to put it on one of those space-times that I showed you. Put it either on Royston-Nordstrom, or you put it on Kerr-Newman. Study the Dirac equation on that curved background, and hope that you will get a similar kind of a spectrum.
Why does that make any sense to do something like that there? Because the size of your particle is really, you shouldn't really put anything. You have a Compton wavelength for your particle,
right?
Which is much bigger than the Schwarzschild radius. So why does it make any sense to?
There is no Schwarzschild radius in this problem. These don't have horizons, right?
I guess what I'm asking is, why does it make sense to use classical general relativity when you have a particle which is? Why does it make sense to treat your particle like a point particle when you have something that's just smeared out over a Compton wavelength?
Well, I mean that's for I'm saying, okay, maybe it doesn't make sense, right? But we're trying to see what can we do, how far can we go with this approach, right? Suppose this was my approach. I had my relativistic quantum mechanics, and I had my Dirac spectrum, and I wanted to just put in gravity, right? The first thing that you would think of would be doing something like this. So that's what people did, right? They said, okay, now I'm going to take the same Dirac equation and put it on Royston-Nordstrom, or put it on Kerr-Newman, and then nothing works. You either get, it's not essentially self-adjoint, or you get no discrete spectrum when it is essentially self-adjoint. And the people who work for that is, for example, Finster, Kamran, Smoller, and Yao. This Yao, right, worked on that, and they proved that this doesn't work. It doesn't come up.
But this is a Reissner-Nordstrom with Q much greater than M.
Doesn't matter. You could put less than M. It still doesn't work. It still doesn't work.
I see.
Yeah.
Okay.
Neither the black hole nor the naked regime would
I
work.
see. Okay.
So that's so something is fundamentally a problem. So possibly that infinite self-energy is to blame here, or part of the blame, because that, you know, as I explained, it shows up on the right-hand side and destroys things. So, and this was, so how can we overcome that? Well, one possibility, there may be other possibilities. We say, oh, I'm quantizing gravity or something like that, right? But something much less dramatic is to look at other electromagnetic laws that can give rise to finite self-energy. What if we do something like that, right? This can be done. So if you had a law of electromagnetism, which first of all for large distances was just like Maxwell, so nobody would notice that it's any different. But when you got closer and closer to your point charge, some nonlinearity kicked in such a way that would make things finite, right? Then it would solve this problem because these objects that you want to couple to gravity are not singular anymore, or at least are less horribly singular, and that could solve everything. And that's indeed, I'm here to tell you that is the case. So let me just briefly, in the remaining time, just talk about that. And there's also another possibility. Another intriguing possibility is that even if you work with classical electromagnetism, a standard one, you can take something called the zero gravity limit, which means that you basically make the geometry, take the gravity out so that the geometry becomes flat. However, remember the topology of these spaces are non-trivial. And so the geometry goes away, but the topology remains. And quantum mechanics is sensitive to topology as well. So you take these Hamiltonians and you put it on the spaces that have a different topology, then you could get a very different situation, different spectrum. And that also happens. So both of these two things we have tried, and they both work. So this will be my last slide, I guess, right? So I will talk slightly about that. So nonlinear electromagnetism, what is that? You have four fields, E, B, D, H, and in order to close the equations, you need to write two of them as a function of the other two. So E as a function of D and B, and H as a function of D and B, for example. Maxwell took the easy way out by taking that E is D and H is B, and this gives you the standard electromagnetics. Nonlinear electromagnetics, which has these problems with self-energy, infinite self-energy. Born's idea was, why don't I put a speed limit so that E is not D, but it's D over square root of 1 plus D squared. So I put something like that, then D is small in magnitude, E is almost D. When D becomes very large, E cannot ever get bigger than 1 in magnitude. So that sort of starts to put a brake on things. And indeed, this theory is called the Born-Infeld nonlinear electromagnetism, and it gives rise to finite self-energy of point charges. So now you're able to couple this to gravity and find the solution to Einstein's equation, which is the cousin of Weierstrass-Nordstrom, but with finite self-energy. And this thing exists. It's called the Hoffman Space-Time, and it has the property, it's very beautiful, is that the ADM mass, the mass you see at the infinity, is equal to the total electrostatic energy of that particle. So the mass is entirely of electromagnetic origin. And now you take your Dirac equation and you put it on this space, and you find out the existence of this grid spectrum. This is what my student did, that's his PhD dissertation. And in fact, it happens exactly what you expected. The spectrum is very, very slightly different from the spectrum of the hydrogen, just by the order of magnitude that it's supposed to be. So things are restored back to normal.
So the speed limit, you are introducing a unit of energy.
Yes, there's a constant in there. So that's right. Yeah.
But because the effect of gravity is so weak, it doesn't matter what value you choose, and you still get the same spectrum.
Yeah, I mean, it will depend very weakly on the Newton constant. Yes, that's right, and on that constant.
You can probably calculate transitions between levels with the emission of the graviton.
Right.
Graviton, excitation of space-time rather than electromagnetic. Did you
I haven't done it, but you're right. This is something that
would be interesting.
My student can do now, right? Yeah, that's it makes a lot of sense. Yeah, to look at that. The fact that you do get a spectrum now allows you to play things like. Okay, so I'm almost out of time, but the great challenge to go beyond the spherical is to go in this theory to go beyond the spherical symmetry, because so far this depended highly on having this particular solution called the Hoffman Space-Time, which is spherically symmetric and static, and therefore it can only model a single particle. So once you have more than one, and we hope to have more than one, is that you cannot just work with spherical symmetry. So, and this is a nonlinear theory, so finding solutions to Einstein's equations is not so easy. So that's something that I would invite anyone in this room who is interested in saying, stop doing whatever it is you are doing and start working on this. So, because this is the future. And, okay, let me stop here, because then I don't want to run over time.
We have time for questions? Yeah.
Excuse me. So I didn't understand when you said that if you put your hydrogen in the background of a black hole, then you say you get a different spectrum. But let's say you take a very large black hole, then if you're just outside the horizon, the curvature is extremely small, so it shouldn't matter. So what size black holes are you talking about?
But it doesn't work, except, I mean,
no,
but
what it
you're
cannot...
saying, I mean, what you're saying is it makes sense, right? And it should be like that, except when people start doing that, it doesn't work. Right? So in other words, you want to do this problem, how are you going to approach it? You have your black hole, okay, right? You have your black hole solution, take your favorite black hole solution. Take Rice-Nordstrom, take Kerr-Newman, take whatever you want, right? And then it has to be charged, right? But then other than that, now you want to put your electron somewhere. Where do you want to put it, right? You want to support your wave function initially outside the horizon, do that, right? But then what you will find out that it will just go in to the horizon, right? You don't get a bound state. Then you say, okay, I'm going to be more clever and put it on both sides of the horizon initially, take the wave function, support it on both sides of the horizon, and this is what Finster, Cambron, Smoller, and Yao did, right? They take their wave function and they assume that it's supported on everywhere, on both sides of the horizon. But then you need some matching condition at the horizon. So they studied that problem carefully, and they proved that that matching condition rules out the existence of any L2 solutions for this. So you don't get any bound states again. That's so obviously something is wrong, right? But that's exactly my point. That's why there was something wrong, and we believe that that's not the right way to do it, and the right way to do it is to go about it in this way.
So if I just forget about gravity for the moment, just think about electrodynamics, in particular QED.
Right.
So a lot of these problems with regards to infinite self-energy and so on are explainable, solvable in QED. And if I write down, so for example, a classical effective description that you would get from looking at loop correction in QED, I would have some nonlinear electrodynamics, right?
Yeah, you get an effectively nonlinear theory. That's what you get.
Right.
But in that theory, the self-energy is still infinite, except it's divergent less dramatically. So when you look at the loop corrections to electrodynamics, right, and you come up with this effective Lagrangian, whatever this Heisenberg, Euler, and Kokel, and so on, right? And then you write this thing down, and the self-energy is still infinite, except it's divergent logarithmically instead of, it was much worse to begin with, right? So, but it still is infinite. So it didn't really solve that problem. So you still have those infinities embedded in your QED or whatever it is you do, and you somehow deal with them. I understand you renormalize, you cut the series off, you put a parameter in there, and you adjust the parameter, and it allows you to do those calculations. But then when mathematicians like me want to understand what is going on, right, we see that it just doesn't make sense because we cannot make sense of it mathematically. That's what I meant. I'm not saying you cannot calculate. You can calculate everything, right? But now that's not enough. You also want to have a theory that's on mathematically solid ground. That's what we are looking for. So maybe it's too much to ask. I don't know. But anyhow, that's what we are hoping to get. Yes.
Very naive questions. So in topological, for instance, the string theory. Even though I'm not a physicist, but anyway, so you have a spectrum of theories that you topologically model, and then these are often kind of invariant under deformations of the underlying geometry of these theories. So if you have singularity types, like conical singularities, if you have a theory and a spectrum that you've calculated first, you can say any other kind of singularity which is deformable to that singularity can also get the same theory and same spectrum. So do you have some phenomenon in here too? Because it's like you're
I hope so.
topologically smoothing
I hope
the
so,
space.
but this hasn't been studied. So you would need to first study those class of spaces which have those particular singularities, right? And then be able to prove some kind of stability result that you can think of. So I agree with the philosophy that you're making, but I'm saying it hasn't been done. I'm hoping now this is the direction we should go. That's what I'm advocating. We should be studying these things. So in other words, we take some branched cover of R3, right? Think of it as your space-time and study your Hamiltonians on that space and see what you get, right? So this is what I'm advocating should be done. We have only taken the first baby steps in that direction. So what we have done, which I didn't get to talk about, is that we took the most simplest case is to take the space R3 branched over the unknot.
Right.
So if you take the R3 branch over the unknot, this is what my colleague and I did, and we studied Dirac's Hamiltonian on that space, and we again got the full spectrum. It's very beautiful and it's very nice. So that's just the first example of that. Now we put it on over some knot and so on.
If you give it complex structure, I mean, this is underlying the space-time is some analog of a variety with an ordinary double point singularity, like a double point.
Right.
The most immediate thing algebraically is the rational double point singularities given by Dinkin diagrams. So you can, I think you can recover all of them.
See, you are a physicist. You were lying.
He's also going to give up everything and do this problem. I have one small historical question. You talked about the Einstein-Rosen paper. Right? They wanted to glue these two things and two sheets, and that's a particle.
Yeah.
I mean, just in Einstein's mind, or Rosen's mind, if there are multiple particles, were they thinking that it's the same second sheet for all the particles, or does each particle have its own sheet?
That's what they were thinking, but we believe that's incorrect. Each particle would have its own double sheet.
Okay.
So if you have n particles, you will have 2 to the n sheets.
But one common sheet in front. Right?
Yeah, you could be in one of them, right?
Our universe
is
one
actually
sheet.
2 to the n sheets.
But then each of these guys has
they're all connected, right? And so that's
I see. Very good.
Okay, so we'll have more time for questions afterwards, and let's thank the speaker again.
You're not a mathematician. You're a physicist.
Yeah, I'll just keep this. No.
I'm getting stuff on the day.
Okay, so our second speaker is Alex Lupsasca. He graduated last year in theoretical physics. He did his PhD with Andrew Sorminger here in Harvard, and now he's a junior fellow at the Harvard Society of Fellows. And he's been working on extreme black hole, new horizon, magnetospheres, and I think he has a nice costume today.
It's Halloween, and in that spirit, I thought I would make your daughter happy, Ivy, and dress as the shadow of the black hole.
We thought you were about to graduate.
No. It's a judge robe. The scary part is at the end of the night when I reveal the naked singularity. So, the paper I want to present today was just released yesterday on the archive. The title is Observational Signature of High Spin at the Event Horizon Telescope. And I have 10 slides, so it should go pretty quickly, but I'm hoping to get lots of questions from people in the audience. So obviously, as everybody knows here, I'm preaching to the choir. It's a very exciting time for black hole physics. We're entering a new era of data. We have all these experiments like LIGO that are detecting plenty of things. And we have the first direct detections of black holes. But so far, in all these detections, the black holes appear as point-like sources. And the existence of the event horizon, which after all is one of the most striking features of black holes, is only indirectly inferred. but we don't yet have an actual detection of the event horizon itself. And one of the things that I find very exciting about the Event Horizon Telescope is that it's going to change that. So for the first time, we're going to have actual images that resolve the black hole on the Schwarzschild scale. And so there's obviously a question. It's a challenge to theorists. The question is, what is it going to look like? Okay, so of course, in general, this is a very complicated question. There's plenty of effects that you have to take into account, like magnetospheres, plasmas, there's jets, there's coronas. It's a very hard problem. But the point of this project was to ask a different question, which is there a regime in which the inverse problem is simpler? So the usual problem is you have a parameter space, you can vary all these parameters and you get an image out of that. And the inverse problem is, given an image, what are the parameters that describe the system? And is there a regime in which, if you look at the image, it's trivial to figure out what regime you're in? The answer is yes. So if you have near horizon emissions from a high spin black hole, and by high spin, what I mean is that I'm going to set A equal to m times this small deviation from extremality, epsilon, and I'm going to do perturbative expansion in epsilon, and work to leading order in the deviation from extremality. So it turns out, if you have a near extremal black hole with deviation set by this small parameter epsilon, then you can analytically compute the observational appearance of, say, an isotropically emitting point source that is orbiting near a rapidly spinning black hole. Okay, so the isotropically emitting point source, that's the Green's function version of the problem. If you can do a point source, you can do anything. But the point source itself, you can think of as modeling, say, a hotspot or localized emissivity enhancement. And what I mean by analytically compute the observational appearance, I mean do the ray tracing and solve the geodesic equation to figure out what the light that's emitted from the source looks like at the observer.
Including the Doppler effect.
Yes, everything. So that's the whole point. Now, generically, of course, this problem is very hard. Ray tracing in Kerr is not possible. It's an intractable problem, a generic spin. But it turns out there's a dramatic simplification when the black hole is spinning very rapidly. And then you can actually do the computation in leading order. And so, well, it's a perturbative expansion, but we only did the leading and subleading order in this expansion in epsilon. And that's what I'm going to show you now. And at the end of the talk, I'll say a few words about why that's actually possible. And there's a very long and interesting story that actually led us to think about these things, which I'd like to conclude with. But I'll spend most of the talk explaining what the result is. And the result has this interesting feature that it's universal, and I'll say a little bit more about what I mean by that. I mean that in a technical sense. But essentially, it doesn't really depend too much on the details of the source. In other words, all that matters is that the black hole is spinning rapidly, and the source is near the event horizon. And the result that we get is generic in that sense. But the precise calculation we did, to be clear, was to have a point source orbiting in the equatorial plane near the ISCO of a rapidly spinning black hole. Okay, so what is the result? The result is that we get a primary image which moves on a vertical line segment. So that's really bizarre. It was first observed, and I think only really discussed by Bardeen in some lecture notes that he published in '73.
Sorry, does vertical line segment mean radial as seen from far away?
Yes. So you're an observer, you're DHT, you're taking a movie, I'm simplifying dramatically, you're filming the black hole, and there's an image that's moving from left to right. So this is what you expect to see. You're in the equatorial plane. This is the axis of the black hole. If there were no gravity, if you just ray traced with actual rays, your flat space-time and light travels in a straight line, this is what you'd expect to see in the situation. You have a bright dot that's orbiting around the event horizon. This is like where you are in the period, and for half of the period, it's moving horizontally across the equator, and for the other half of the period, it's behind the black hole and it's secluded. So that's what you naively expect to see if you don't think about gravity. Now, what I'm telling you is that actually the answer is literally orthogonal to that. You get a vertical line segment, which I'm going to show you in a second, and all the light that comes out, all the electromagnetic emissions from this near horizon region, are constrained to come out on this line. And that's a completely generic result that just arises from the fact that the black hole is near extremal, and you're emitting from the near horizon. And I'm going to give you a nice picture at the end to make that more intuitive. Now, in gravity, because the space-time can curve the trajectories of photons, you can also get relativistic images, these so-called secondary images, which typically are very faint. in this limit, actually what happens is that you get a divergent number of secondary images. So the space-time is maximally warped. This is as bad as curvature can get. And so you get more and more and more and more images. So if you take epsilon to 0, you approach maximal spin. There's actually the divergent number of images. And a huge part of the challenge of this project was to extract the primary image. But first we had to compute all the images. And I'll show you some plots of what that looks like. But the primary image moves on a vertical line segment. I'm going to it's a pretty striking signal. The secondary images actually also do something quite interesting. They have a rich caustic structure. So a caustic arises, for instance, when you have multiple light rays that intersect. And because there's more and more light rays, they intersect more and more as you take epsilon to 0, and so it becomes a total mess. And typically, well, that means the geometric optics breaks down, so it's no longer valid to solve the geodesic equation to describe the ray tracing. What you're supposed to do is instead go back to wave optics, and the photons actually diffract. That's a really hard problem, which we didn't solve, but we could say what happens with these caustics. Essentially, this entire line segment lights up. So that's something that could also be seen. And that's very exciting because we think this is a smoking gun for a high-spin black hole. So if you see that, you know that you're likely looking at a high-spin black hole. So this is the actual output of the calculation. On this plot, I'm only showing you the primary image. So here we go. This is where we are in the period. For most of the period, actually, the primary image is not visible. Then it suddenly appears and zooms down the neckline. So on these plots, I'm showing you the location on this neckline. But this is the shadow of the black hole, which, when the spin gets very high, becomes squished and develops this vertical line segment. And the simple prediction is that all the emission from the near horizon region is constrained to come out on this line, okay, at the edge of the shadow, the vertical edge of the shadow. And what I'm showing you here is the position of the image, its track, as a function of the height on this line.
Is that dot changing in brightness?
Yes, so the opacity of the dot on this image is proportional to the second graph here, which is the flux. So this is the observed flux that you would actually measure, divided by the Newtonian flux, which is what you would see if space-time weren't curved. And so that's just a trick to abstract away the details of the source. It's just saying if you have a Newtonian source and you expect to see flux F Newtonian, then instead what you get is flux observed, which is multiplied by this factor.
And what's the orbital radius for the orbit?
So this is a source which is very near the ISCO.
It's a stable.
It's on a stable circular prograde orbit near the ISCO. In fact, it has to be very close to the ISCO in a technical sense, which I'd rather not go into, but it doesn't quite depend too much on the details. Again, it's a generic result. So this is the flux, observed flux over Newtonian flux, and I've also divided by this factor epsilon over log epsilon, which is how the overall flux scales in this deviation from extremality. And finally, this is the redshift factor of this image. So by redshift factor G here, I mean the ratio of the energy observed divided by the energy at the point of emission in the local frame of the emitter. It's related to the other redshift factor Z by G is 1 over 1 plus Z. And the key thing to note here is that typically people say that the near horizon region is a region of infinite redshift, but actually the primary image is highly blue shifted. And the blue shift can peak all the way up to square root of 3. So if you had something emitting, say, with a peak at the iron line, which is 6.4 keV, you would expect to actually see a peak in brightness at square root of 3 times that, which is this peak here. That's around 11 keV. And then,
before we take this away,
yes,
it looks like the area under the curve, we get more photons than we would naturally get, because you get 80 times the peak.
Yes, but I've also divided by epsilon over log epsilon. So as you take epsilon to 0, the image gradually shuts down. It just darkens and disappears, but that happens pretty slowly because of the log epsilon. So here I've rescaled. So for instance,
so overall, do we get more photons or less compared with the case without gravity?
So it depends on the spin. Generally, a little less. Yeah.
And as epsilon gets smaller and smaller, and you approach extremality more and more, eventually you get vanishing flux. So there's precise formulas, but these formulas are rather complicated, so I didn't display them.
Your qualitative result that's interesting about blue shifts, that must really rely on this extremality, right? Because it's the fact that you have the ISCO is coinciding with the photon orbit in your picture, right?
So that's right, and it's exactly what Avi was saying earlier. Essentially what's happening is that you've got a particle on the ISCO, and it can send light forward. In the local frame, of course, the light is moving at the speed of light, but what that means is that it's actually infinitely blue shifted, and it comes out with very high blue shift. That's what's really going on. So I should say, in this problem, we can describe the point source that's orbiting, and we can go to the local frame of the source, and the output of this calculation is that if you're someone, say on a star orbiting near the ISCO, you can tell me, I shine the flashlight in a direction, and I can tell you as a function of where you shine the light, I can tell you where it appears on the screen of the observer, and which direction you have to shine it into in order to reach the observer with parallax.
So maybe you already said this. What breaks the symmetry of the problem? Why is the dot moving down instead of heading?
So I'm here. I'm actually not exactly in the equatorial plane. It turns out exactly equatorial observers, that's highly singular. You have to solve a slightly different equation. So yeah, I'm a little bit above the equatorial plane. I'm actually at an angle of 84 degrees.
84.
So from the axis of rotation. So I'm 6 degrees off the equatorial plane.
So if you were right in the equatorial plane, you'd expect it to just appear in the center and then disappear, right?
So
it can't go up or down.
So the image is reflection symmetric when you're exactly equatorial, but actually also when the spin epsilon, the deviation from extremality goes to 0, it actually becomes reflection symmetric again. So if you're near extremal enough, actually it doesn't really matter what angle you're at. I should say that this neckline, actually we've computed precisely, we call this the neckline, but this line, it shrinks as you move out of the equatorial plane, and eventually there's a critical angle, which is 47 degrees from the axis, at which you no longer get emissions at all. This line is completely closed up. So in order to see this signal, you need a rapidly spinning black hole, and also you need to be not exactly in the edge-on case, but you need to be in a band of a few tens of degrees around the equatorial plane. So if you're looking down the barrel, if you're in the face-on case, you wouldn't see this. There is no neckline in that case. But there's a wide range of parameters. Okay, so that's the primary image. Let me just briefly show you the secondary image. The secondary image is plural. So when you actually solve when you do the calculation, you get something like this. So this is a mild spin of, so here the spin of the black hole is 99.99995% of externality.
That's mild.
Yeah. I mean, epsilon is small, but I'm going to show you later also the Thorne limit. So a black hole at 99.8% of externality. And the results are qualitatively similar. What happens is that as you take epsilon to be small, actually the calculation gets messier and messier because the number of images and tracks that you get here gets larger and larger and larger. So here the primary image is actually now in green. So that's the one that you just saw earlier. It has this nice little peak in the flux. And here you have this garbage, which is basically due to these geodesics intersecting, which introduces caustics. And in this geometric optics approximation where we describe photons by geodesics, that leads to caustics, in which the flux is formally divergent. Technically, you're supposed to resolve that by doing wave optics, so that's a very hard calculation. But one thing I can tell you is that the reason the flux diverges is because when the light rays intersect, actually the images, they want to stretch out and completely fill this neckline. So the secondary images have the effect of giving bright flashes over the whole neckline. But we can't quite say exactly how bright because the calculation doesn't tell you the approximation breaks down. And here are the redshifts. So it turns out 1 over square root of 3, which is about 0.6, that's the sweet spot at which most of the light comes out. The brightest image is highly blue shifted, but most of the images, and again, like there's a divergent number of images that appear here as you approach extremality, they're going to be a redshift of of 1 over square root of 3. So if you have something that's emitting at the iron line, 6.4 keV, that could lead, because of these bright caustics, these flashes, to a lot of emission at about 3.7 keV. So those are
so is that
two frequencies.
People have done a lot of simulations of relativistic iron lines. Like the relativistically broadened lines are a signature of some high-speed cases.
Look at the images.
Yeah, but he's talking about the spectrum of it, right? So you should still. So do they get the same spectrum that you get, or have you determined what the spectrum would be for iron?
So in a paper that I'm working on now with Lily, who's here, we're actually trying to. This is the Green's function of the problem. So then we're saying, okay, let's suppose that now we have not just one point source, but we have an accretion disk of many point sources. We filled out the disk. Now can we compute the spectrum in G? And the answer is we're going to get. There is an answer. We're going to compute it. But I think unless your spin is incredibly high, that spectral curve that people measure is dominated by emissions that are far away from the horizon. So the answer is I think we can compute it, but it's probably a tiny part of what is commonly measured for a not maximally spinning black hole, and that is as the black hole spin increases, it'll become a greater and greater, a more relevant proportion of the total spectral curve that is measured.
But you may get interesting effects from these, like that green redshift image there, where what they really try to use to measure the spin is the red wing of the line. So you may actually get an interest, even if most of the emission comes from far away. You may get some interesting modification to the program.
Yeah, we're thinking about this. So I don't want to make a definitive statement because we haven't finalized the paper, but we're gonna try to say what that is. And the other direction that we could push this into, which we haven't done, is to describe polarization. So it turns out once you've done the ray tracing, it's actually trivial to add on polarization on top of that. You just have to tell me what you think the polarization is at the source, and given all the formula we have, it's trivial to tell you what the polarization is at the observer. We just didn't do that in this paper because we didn't really know what polarization to pick at the source. But if you have a favorite polarization that you're interested in studying, just tell us what it is, or look at the formulas in our paper, and you can trivially add it on.
But by the way, one last thing. Yeah. If you had an inhomogeneity in the accretion flow, like if you had a hot spot or something like that, then that could dominate.
Yes.
Even if you had a physical case with an accretion disk.
Yes.
If you had some magnetic heating or something like
exactly.
that.
So
that could still, it might be dominant. I don't know.
Right. So the period of this process is 4 pi times the mass of the black hole. And I think roughly for something like Sagittarius A*, which probably, okay, maybe it's Sagittarius A* is unlikely to be spinning very fast. This is on the order of minutes, so this primary image, the brightest one, you'd see a flash that would last for maybe a minute. So I don't know what you expect to see, if this is something you could see, but that's the kind of signal that you're looking for. So a quick slide where I'm showing you how this calculation varies with different deviation parameters for the deviation from extremality. So here, this is epsilon equals 0.15. This corresponds to a black hole that is at the Thorne limit of 99.8% of extremality. And here I'm just dialing up the spin. The key point I want to show you is that, in fact, you get more and more images, which I'm not showing here, but the brightest images have roughly the same behavior in all of these plots. There's high blue shift, there's a peak in the flux from the primary image, which zooms down the neckline. So this is pretty robust and not exactly dependent on spin, as long as it's high.
How big an epsilon can you push before you
use
this theory?
So this is just perturbation theory.
I know. Can you use it at 0.5?
Well, okay, the principled answer is that I would have to compute the next terms in a perturbation expansion and check when they get large. This computation is fiendishly difficult, so I'm not going to go to higher order of perturbation expansion.
Someone that did the full thing.
Yeah, I mean, I think at some point, if epsilon goes to 0.5, I think you can definitely ray trace it. So, for instance, this photon here that gives you the peak in the flux, it actually spirals around the event horizon about 20 times before it escapes. So this is light that's zooming around in a crazy way, and I did check this numerically in my very low-tech kind of way, and you need to keep many decimals to see this. It's a little tricky, but surely as epsilon gets large, these kinds of insane effects disappear, and then you can just do the usual ray tracing that people here are experts at doing, and so you should be able to match onto this smoothly.
And one other thing is if the light really does have to go around that many times, then you need to be in some kind of optically thin regime. I mean, there can't be stuff around the black hole.
Caveats, that's true. But the light, I think, tends to orbit around the poles. It doesn't necessarily go through. Okay, it depends. There's different trajectories. But yeah, that's a fair point. That's a fair point.
Well, I mean, the light's going up at high azimuths around the pole of the black hole?
Some of it does. So it's really complicated. I can show you the details.
Well, that would certainly be important for the iron line case, right? Because anytime you pass through the equatorial plane,
yeah, I think if one wanted to, there's a paper from '76 by Cunningham who tried to describe what happens when the light hits the disk in the equatorial plane again, and it turns out that it's not so difficult to incorporate. You get some extra factors in the so-called transfer function. So in principle, you can also take that into account. We haven't done this. This is the easiest version of the problem, and there's a signal which is pretty robust. Of course, once you start to add tons of different things, it becomes more complicated. But in this regime, generically, you can actually do calculations exactly and solve the equations. So that's roughly the prediction, and I want to spend the next 5 minutes at the end of my talk to explain why there's a reason why this calculation is possible, and why this result is robust, and what I mean by universality.
This epsilon business.
Yeah.
So you said that you need to be close to the ISCO to do your theory.
Yes.
But I presume how close you have to be is a function of epsilon, or is it some other parameter?
Excellent. So let me address this. So this is a plot from a paper from '72 by Bardeen, in which they plotted as a function of the spin, what is the location of these physical radii, like the ISCO, which here is called RMS, the photon orbit, our photon, the horizon, R+, and then so on and so forth. And here there's a line, there's a radius which is constant and independent of spin, and that's basically the radius of the ergosphere in the equatorial plane. That turns out to be independent of spin. And the reason I want to show you this is that as you dial into extremality, as you take epsilon to 0, which means you approach a over m equals 1, all these radii converge. And that doesn't mean that they're actually very close to one another. It just means that the Kerr metric, which we usually describe in Born-Oppenheimer coordinates, as a coordinate singularity there. And what you're supposed to do is take a scaling limit where you zoom into the horizon and you actually resolve these scales. Because what's really happening physically is this picture. So as you crank up the spin, all of these radii, they approach r equals m in Born-Oppenheimer coordinates. So you think they're on top of one another. But actually what's happening is that the proper radial distance, as computed using the Kerr metric, between them begins to diverge. So for instance, R0, which is the edge of the ergosphere, we call this the mouth of the throat, it actually becomes infinitely far away from the ISCO, which is deep in this so-called throat, and the ISCO itself becomes infinitely far away from the event horizon. So in the Kerr metric in Born-Oppenheimer coordinates, all these radii, all these scales look like they're at the same place, r equals m, but actually they're infinitely far away. And the region near the event horizon, this near horizon region, actually acquires an infinite volume. It becomes a space-time in its own right. It solves the Einstein equations by itself. And if you cut it off here, and you just look at this throat as a space-time in its own right, it actually looks very much like anti-de Sitter space, which is something that you've heard about a lot here because it's the so-called gravitating box, which is dual to CFT, and then we can say some things about quantum gravity. And I will return to this in the last point I made. So the idea is that the black hole is a puncture in space-time, and as the spin increases, the depth of this throat before you hit the singularity actually increases. And one way to understand why there's a maximal spin, why A cannot exceed m, is that when you go to that limit, the throat becomes infinitely deep. And again, as I said, you can truncate the space-time here and just consider this near horizon region. And you see, going up and down this throat is really going to smaller or larger radii. So of course, once you cut off this infinite throat, it's an infinite cylinder, which has a new symmetry. You can go up and down the cylinder because it's infinite. You have translation symmetry along the cylinder, which really physically, when you map back to the black hole space-time, means you have a scaling symmetry as you zoom in and out of the horizon. And it turns out you can show, using only general relativity, that not only does this happen, but in fact, the scaling symmetry is in some sense a local scaling symmetry, and there's an enhancement to an infinite dimensional conformal symmetry. So why am I interested in this? It's because that is a tool which is very well studied in other areas of physics, for instance, condensed matter physics, where you sometimes study systems which have a critical temperature and display critical phenomena. And the diagnostic for criticality is the emergence of conformal symmetry, which is exactly what happens here. And this is not just a mere analogy, and this is my last slide. The point I want to make is that the maximally spinning black hole you can actually think of as an example of a critical point in astronomy. So usually in physical systems, like say a magnet, you've got a bunch of spins that are correlated. And typically what happens is that they're correlated on a certain length scale. But there's this thing called a critical temperature that you can reach by changing the temperature, magnetic fields, adjusting various parameters in the model. And when you actually dial your system into this critical temperature, what you'll find is that the correlation length, the typical length scale on which the spins are correlated, it diverges. And that means that the system develops a scaling symmetry because it's correlated on every length scale. It looks the same at every scale. You can zoom in or out. It looks the same. And moreover, you can look at different patches of the system and zoom in and out by different amounts in different patches, and it still looks the same because it's the same at every length scale.
Is there something that corresponds to phase, to different phases?
So, yes, that's a good question. That's a little technical, but in this case, the extremal black hole, which is where the phase transition happens, has 0 temperature. So it's an example of a quantum phase transition because at 0 temperature, there's no thermal fluctuations. The only fluctuations are quantum. Mm-hmm. And it's an active subject of research to try to explain how these arise in the theory of quantum gravity. But the simple point I want to make is that just like in these systems where you have an emergent local scaling symmetry, which we call local symmetry, the conformal symmetry, the black hole actually also has a divergent correlation length. So it turns out that if you have a black hole with this spin parameter regulated by epsilon, the proper depth of the throat, d, is given by this formula. So as epsilon goes to 0, the proper length down the throat is diverging. So that's the precise formula that relates the depth of the throat to the deviation from extremality, and as the black hole becomes exactly extremal, the throat becomes infinitely deep, and you have this emergent infinite dimensional conformal symmetry. Now the reason this is useful in condensed matter systems is because it turns out that when you're near that critical point, when you're near the critical temperature, the behavior of every field becomes a simple power law of this type, like the correlation length, and the exponent here is called the critical exponent, and it turns out that there's a finite number of critical exponents that completely describe the behavior of the theory. And this is a long story that I'm not going to go into, but the point is that the critical behavior of fields in the near horizon of rapidly spinning black holes is also universal. It's the same kind of mechanism. You can write the formulas in a way that it looks exactly analogous to the condensed matter story. So you dial up the spin, that's like dialing the temperature. In fact, in black hole thermodynamics, taking the spin to be maximal, that really is taking the temperature to 0. You have a divergent characteristic length of the system. In a statistical system, that would be the correlation length. Here it's the depth of the throat. And then you can basically expand in this parameter. And the leading order behavior near extremality in this epsilon expansion is fixed by this symmetry. The symmetry is exact when the black hole is exactly extremal. When you are slightly away from extremality, it's only an approximate symmetry, but it still controls the approach to the critical point. Essentially, the behavior I was showing you before is really insensitive to the details of the source, as long as it's deep in this throat. Really, as long as it's deep in this throat, the light has to come out on this neckline. It just follows from that. It's a constraint from the symmetries. You've frequently seen in talks this year discussions of ADS-CFT. ADS-CFT is a conjectured holographic duality that relates a gravitating box, this anti-de Sitter space-time, to a putative dual conformal field theory. And of course, as far as I can tell, we can't actually probe ADS because we don't live in that universe. But unlike ADS, this near horizon geometry is realized in nature when you actually go near the event horizon of a rapidly spinning black hole. And this is a signature of the same kind of conformal symmetry that you see emerging in ADS. So as a high energy theorist, that's also really exciting because if the event horizon telescope sees this kind of signature, it's really a signal of this infinite dimensional conformal symmetry of a gravitating box. That's realized in nature. Okay, so I'll end here and take questions. Thank you.
I think I remember Sam gave a talk a while ago where he was talking about gravitational waves, maybe very close to externality, something like that quasi-normal modes are high amplitude for a long time or something.
So the way this effort started is that we started deep in the theoretical side with these symmetries, and we eventually understood in the paper that we wrote last year also with Sam and Andy that there was universality and you could describe the behavior of fields in this regime by simple power laws, etc., etc. And we've been trying to make contact with experiment. So we have a tool. We can't do like Schwarzschild or a spin of 0.5. We just have this amazing mathematical structure that emerges near externality, and that's the one tool that we have. And we've been trying to, go from this interesting theoretical insight towards making predictions for experiments. So we're constrained because the tool only applies in a certain regime. But when you're in that regime, it's turned out so far that you can basically do any calculation. This one turned out to be really gory. It was much worse than we thought it would be when we started. But essentially because the symmetries, in the end, you can do it. And you can do the exact same thing with a gravitating source.
I just thought there was like a very distinct signature. I mean,
exactly.
You already ruled that out from the LIGO detections, for instance. You already know that the stellar mass black holes that they're seeing are not this, epsilon is very small.
So just like here we put a point source that was emitting electromagnetic emissions, you can do the same problem and have emission of gravitational waves. And there is a signature, again, of extremality in that regime, where instead of hearing the sound that we heard at LIGO, you get a long-lived warble. And the thing about that, though, is that if you ask how near extremality you have to be to hear that distinctive pattern where instead of going whoo, it goes whoo, you actually need to be at 99.999999999%. There's like 10 nines or 50 nines that you need to be before you actually really hear that. So the point is that these expansions around extremality, they're mathematically powerful. You can always compute anything, but there's no guarantee in general that the signal that you get will survive as you take epsilon to be larger, as you take the deviation from extremality to be larger. But here, fortuitously, this is somewhat different from the gravitational case. That was the point of these slides, that already this value of epsilon here, it corresponds to a black hole that's at 99.8% of extremality. That's the form limit, which people believe can be reached. And the point is that this signal is still present there. So I hope that addresses the question.
Okay, so we'll have pizza at 4 for people who have more questions for our speakers. And let's thank them.
Thank you.